Hello, do you hear me?
Hello, Dr. Hafiz.
Yes, can you hear me?
Yeah. We can hear you.
Sorry about
We'll
that.
start. We'll start in around 5 minutes from now.
Sure. I wanted to join a bit early, but my internet is a little bit unstable today. So apology in advance. I may actually cut down anytime. So in case that happen, just wait for me. I'll reconnect.
Okay.
Yeah.
Okay. We'll start in around 5 minutes. Exactly at 6:30 we'll start.
Sure.
So,
country
Okay, just a minute.
Thanks.
Okay, good evening, friends, and a very warm good morning to our distinguished speaker for tonight, Dr. Hasnain Hafiz. Before we start, let me just give a brief introduction of Dr. Hafiz. Dr. Hafiz, he did his MSc Physics degree from Dhaka University, Bangladesh, MS and PhD degree from Northeastern University, Boston, USA. He worked as postdoctoral research associate at Carnegie Mellon University, USA during 2018 to 2020, and is currently working as postdoctoral research associate at Los Alamos National Laboratory, USA. Dr. Hafiz has developed an atomistic modeling approach to transport and reaction phenomena in structured electrodes for fuel cells and related application. He has also developed a methodology to interpret high-resolution transmission electron microscopy beam damage on a catalyst surface and related surface corrosion at finite temperatures. Further, Dr. Hafiz developed DFT-informed activity and durability descriptors for state-of-the-art PGM-free oxygen reduction reaction electrocatalysts with Me and C, where Me is either iron, cobalt, or manganese, active sites to interpret degradation mechanism and guide synthesis routes for more active and durable electrocatalyst material. Dr. Hafiz has so far published around 30 papers in reputed peer-reviewed journals, and his Google Scholar citation is 734. With this brief introduction, may I now invite Dr. Hafiz to deliver a talk. The title of his talk is A New Atomistic Paradigm for High-Capacity Lithium-Ion Battery Materials. Dr. Hafiz, you may start the talk. You are welcome.
Thank you. Thank you very much for this very nice introduction. And thanks the organization committee to invite me here. And I'm really, really honored to present some of my work today and share some idea that we have developed over the past couple of years. So let me share my slides. Can you see my slides well?
Yes, it's visible.
Okay, you see the welcome slide, right? It's written a new atomistic paradigm for high-capacity lithium-ion battery materials. Yes, hopefully I'm in presentation mode because I have issues previously with Zoom, but I think you can see the presentation slide very well. So yes, so let me just move on. You have already given a very good introduction. I did my PhD from Northeastern University, Boston, and then I went to Carnegie Mellon University in Pennsylvania. And then since before the COVID starts, I joined Los Alamos National Lab, and I have been working there since then. Now, my research interest focuses mainly on the design of materials for clean energy demand. And my work, let me just make it a pointer. There's a pointer. Okay. So as I was saying, like, my research interest mainly focuses on the design of materials for clean energy demand. My work connects theory and simulation with spectroscopy, and more recently in scientific machine learning for the rational design and development of materials for energy applications such as lithium-ion batteries, fuel cells. My talk today will mainly focuses on my work on lithium-ion battery materials, and I will discuss today how we developed a new atomistic paradigm for lithium-ion batteries, mainly applicable to very demanding need for electric vehicles or even electric aviation. And I will describe like why we need that and how we have developed these techniques and methods, and open up these ideas about this new paradigm in a quantum mechanical perspective. Now, here is a list of some papers that we have developed over the years, published for only concentrating our work on battery materials, but using spectroscopic techniques such as Compton scattering. We have also actually used other spectroscopic techniques such as X-ray absorption, emission, and all sort of different things. But today I will just focus on my work on Compton scattering. And I will mainly describe our very recent work that is published in Nature this year. So here is my list of collaborators, advisors, mentors for these projects. You probably know Professor Arun Bansal from Northeastern University. He had a talk, I think, 2 days ago, and he was my PhD advisor, and I'm still collaborating with him. Professor Bernardo Barbellini is now working in Lund University in Finland. He has a very good knowledge in Compton scattering theory. Professor Kosuke Suzuki is right now a professor in Gunma University, Japan, and he is the key experimental collaborator for these projects. And he mainly works in Spring 8, Japan for all of his experiments. And Professor Venkat Viswanathan is a associate professor in mechanical engineering, Carnegie Mellon University. And he has been joined recently for this project. And he was also my postdoctoral mentor during my stay in Carnegie Mellon. Besides them, we are actively collaborating with Spring 8, such as people like Yoshihiro Sakurai from Yokohama University. Naoki Yabuchi also collaborating with us. He synthesized different materials. And Professor Hiroshi Sakurai is also actively involved. Now, here is the outline. I will try to give you some idea about the history, development, and challenges in battery technology. And then I will tell you what is lithium-rich cathodes and try to explain the high capacity these cathodes have. And then I will go over Compton scattering, spectroscopy, and its application to lithium battery cathodes. And finally, I will discuss the anionic redox mechanisms in lithium-rich materials such as lithium titanium manganese oxide. And finally, I will conclude my talk. What is the format of the talk? Are you going to ask question at the end, or you can actually feel free to ask me a question anytime?
So you will have a talk of around 50 minutes, then we'll have a short discussion afterwards.
Okay,
after
okay,
the
thank
talk.
you. Okay, thank you. All right. Brief history of batteries. You can see here that the batteries have come a long way since Volta stacked this copper and zinc disc together around like 200 years ago. Since then, the battery technology has continued to evolve from lead acid to lithium ions. And here the lithium's weakness is its reactivity, which is in fact its also its strength. So in the early 1970s, Stanley Whittingham used lithium's this enormous drive to release its outer electron and develop the first functional lithium battery. Then in 1980, John Goodenough invented a more powerful and useful battery by choosing cobalt oxide as a cathode, which actually doubled the battery capacity. In 1985, Akira Yoshino replaced the lithium metal anode with a carbon-based material and invented a battery wholly based on lithium ions. His battery was the first safe production viable lithium-ion battery, which became used widely in cellular phones and notebook computers. So they made the lithium-ion battery workable in practice and applicable to many everyday devices. And then they finally received the Nobel Prize in Chemistry in 2019. Now, while the battery technology came a long way, starting from rechargeable lead acid in 1859 to recent high-capacity lithium-ion batteries, the science behind this technology, the science underlying battery technology is often criticized for its very slow development. For example, if you compare the semiconductor industry, where Moore's law predicts a doubling of memory capacity every 2 years, energy storage took like hundreds years to double energy density from this lead acid to nickel metal hydride. So even though the progress with lithium ions in last few decades are very promising, it is still cannot keep the pace with the semiconductor industry. Especially the current demand for the electrification of heavy duty vehicles and aircraft will require batteries with more energy density than the existing batteries at the market. And we certainly cannot wait another 100 years for a paradigm shift in battery technology. So in fact, if you see the US Department of Energy's projected goal, then you'll find that on the left side, you will see the lithium-ion battery demand on the y-axis, and right on the x-axis is the different years for next 1 decade. And you will see that the demand is exponentially growing. So by 2030, the demand will be really, really high. And the consequent cells in electric vehicles will also rise exponentially globally, as analyzed by Department of Energy's Federal Consortium for Advanced Batteries. This suggests that the next generation batteries will need to store a lot of energy, and we need to have new strategies to increase the energy density of electrode materials. Looking at the existing lithium battery industry and applications, we see that lithium is not the only metal used in lithium-ion batteries. There are like many cathode types, and they all have different formulations and applications. We certainly see that the current lithium battery industry heavily depends on the supply chain of transition metals such as cobalt and nickel. Such high demand of cobalt and nickel also reflects on the cost, the raw material cost of battery cathode, and which are very critical for current industry. And you can see that their prices are really, really high compared to other more abundant materials such as titanium, aluminum, or manganese. Therefore, a significant attention goes to this kind of low cost, more abundant materials. Yes, if you have any questions, just let me know. Otherwise, I'll just keep going on. So our target is to use this kind of more abundant but less expensive materials and try to, but not compromising the battery capacity, and try to find out whether we can make such things and have the idea about underlying mechanisms that can drive. Okay. All right. So okay, not to mention that such critical supply of raw materials also have consequences in geopolitical and environmental issues, which are very concerning for us. And to overcome these issues, like the challenge in the battery industry and the increase of the raw material cost and the consequent political changes in Africa and the other countries, like there is a global scientific efforts on the development of new battery technology, which also reflects on the number of papers published each year relevant to batteries. As you can see here, the number of published paper on the right side. Here the paper searched from the Web of Science from 2000 to 2019. The insert displays the percentage of papers published for different batteries from 2015 to 2019. So you can see that there is a global surge of research work in battery world, and that also reflects in the publication. Now, I will discuss about some of the batteries available in the market and their capacities. The capacity of a battery is defined as the amount of energy that it can deliver in a single discharge. Here shows a list of some well-known battery cathodes with their capacities like lithium manganese oxide, lithium iron phosphate, lithium cobalt oxide. So this the first commercialized lithium ion battery is this lithium cobalt oxide, and I'm talking about the cathode side, of course, which is the positive side. Today I'm not going to discuss about the anode, and this material is a layered material, and it remains as a stellar electrode for 2 decades. By partially substituting cobalt with nickel and manganese, we can prepare lithium, nickel, manganese, cobalt, or NMC cathode, which displays a capacity of 200 milliampere hour per gram. Additionally, some substitution of cobalt with lithium within the metal oxygen layers allowed us to make lithium-rich NMC that exceeds the theoretical capacity based on the redox activity of the cationic network. Now, the search for high capacity electrode evidently proposed other type of cathode materials where we do not use like this nickel or cobalt, which are very expensive. Here today I'm proposing this material that is disordered rock salt, lithium titanium manganese oxide, which does not contain expensive cobalt or nickel, but shows even superior performance in capacity. The marked difference in capacity in lithium-rich cathode is explained as a joint cationic and anionic reversible redox process, which I will explain in next few slides. I will highlight on the technical details on cationic and anionic reversible redox process, and I will show you how we can open up a new atomistic paradigm. First, let me remind you the underlying reaction process in a lithium battery, which involves an oxidation and reduction reaction. This redox process involves transfer of electrons between 2 species. For example, in a lithium-ion battery, current is generated when conduction electrons from the lithium anode are transferred to the redox orbital of the cathode material. And this redox orbital can be cationic or anionic, depends on the structure and symmetry of the materials involved. And the ability to visualize and and to find out how these orbitals evolve under lithiation and delithiation process is very important to understand how a battery works and to design new battery materials. Now, to understand possible explanation of high capacity, we compare between classical layered oxide materials and this lithium-rich NMC material. You can see that the classical material is actually a lithium cobalt oxide. It has regular arrangements of this anionic framework and the cationic framework, and the lithium sits in between these two frameworks as layered. And then the overall redox process is a one redox process. You can see the very symmetric voltage curve, and this is actually all the reactions happening here is only the metal atom involves in this case. On the other hand, in high capacity layered materials like these NMCs, we see an additional lithium in the cationic framework. And because of that, if you have the voltage curve, we'll see that then additional step here. So it is no longer this very symmetric step. And this is because what happens here is, like, first we have a cationic redox and then we have an anionic redox. So oxygen also participates at some point. That's why we can go to the extra mileage and we have a higher voltage curve in this case. And this new redox is actually oxygen redox, as I mentioned. Now we consider the Lewis configuration of oxygen electronic structure, which shows 1 2s and 3 2p doublets, where this 2s stays deep in energies and becomes redox inactive. Only these 2p orbitals involves in the redox process, and this high energy 2p orbit doublets participates in metal and oxygen bond formation, where their involvement depends on the the local structure of the material. In traditional layered material, in lithium cobalt oxide, as I mentioned earlier, each oxygen is coordinated with 3 metal neighbors. Like as you see here, this is the oxygen and it has 3 different metal neighbors. As a result, all 3 2p orbital oxygen 2p orbitals engage in metal oxygen covalent bond formation, and we see this stabilized metal oxygen bonding bands that rise below the Fermi level, and this anti-bonding band that stays near the Fermi level. And this anti-bonding band is responsible for the redox process, because all the electronic the charge transfer happens in this anti-bonding band at the Fermi level. On the other hand, lithium-rich compound contains an extra lithium within the metal layers. Therefore, the oxygen 2p orbitals that points toward a lithium atom is weakly bonded because of its small overlap with the lithium 2s orbital. As a result, it behaves like an oxygen non-bonding state, and it is located above the stabilized metal oxygen bonding band. This non-bonding oxygen orbital is also called unhybridized or orphaned oxygen 2p states, since it doesn't participate, like it doesn't make any bonds with the metal bond, and it just stays like an atomic state near the Fermi level. Now, why this non-bonding oxygen orphaned state electrochemically very so interesting? Why? The reason is in classical system, in this case, this metal oxygen anti-bonding band at the Fermi level is responsible for electron transfer, and an extra electron can only come from the this stabilized metal oxygen bonding band once this anti-bonding band is empty. So therefore, it makes some destabilization in case you want to take out an electron from this bonding band. Where in lithium-rich system, besides this metal oxygen anti-bonding band at the Fermi level, we have an additional band right next to it, this oxygen non-bonding band, from where we can take some electrons out without making any structural destabilization, and this metal oxygen bonding band remains like intact. So therefore, understanding this oxygen non-bonding orbital and where it is located is very important for the design of high capacity batteries, especially how this oxygen orbitals evolves during charging and discharging process. and how it interacts with the neighboring metal oxygen bands need to be realized experimentally, which has been very difficult to understand fully with known experimental probes and techniques, such as X-ray absorption or X-ray emission. This kind of techniques has been very difficult to understand this non-bonding oxygen band. So that's why we use Compton scattering in our study. We have been actually pushing this the use of Compton scattering to battery to understand battery mechanisms for a while. This is just our latest work, but I will also give you some idea about some previous work. So in our study, we use Compton scattering spectroscopy to understand the behavior of this oxygen 2p states that is crucial for lithium-rich cathodes. This shows a cartoon of Compton scattering where X-ray photons strikes where X-ray photons strikes electrons of a sample, and we can detect the spectrum of the scattered photons, which is related to quantity called this Compton profile. This Compton profile can be constructed using electron momentum density distribution, which is related to the electron wave function. As a result, Compton scattering can access both energy and momentum characteristics of the electronic state, which is not that easy, to get using other spectroscopic technique, such as as I mentioned about X-ray absorption, which can only access the energy characteristics, but cannot get the momentum characteristics, where in this case that is possible. Moreover, because of the involvement of the wave function, this technique is sensitive to the bonding properties of materials, which can detect weak bonds such as hydrogen bonds, and it can differentiate these bonds from purely electrostatic interactions. Now, this is the setup that my collaborator in Spring 8 Japan have used for the experiment. I'm not going to go over the detail, of course. My part was mainly on the theory side, but just to show you that this is the main setup in Japan. Now, before going to our discussion on the lithium rich, let me first show the strength of Compton scattering by showing its capability in macroscopic scale. Compton scattering uses high energy X-rays as incident and achieve a high penetration depth and enables bulk sensitive measurements. In this work, Compton scattering is used to this Compton scattering is used to map the lithium distribution in CR2032 battery. We construct a parameter called this S parameter using the Compton profiles, and we can actually show a linear relationship with the lithium concentration in a battery with this S parameter. You can do also all sort of different theories. All of them actually agree very well. And this image shows the X-ray transmitted image, and the intensity of Compton scattered X-rays over time, and we see the diffusion of this lithiums from this negative electrode to this positive electrode, which results a volume expansion over time. As you can see that this separator, it moves toward the negative electrode, toward the anode, because as the times goes on, lithiums diffuse through the cathode, and then cathode have a volume expansion. So we can then track the S parameter in a certain area of this battery over time, and this can be used with this previously derived relationship with the S parameter and lithium concentration, and from using that linear relationship, we can also get the distribution of lithium over time. So this gives you some straight idea about the state of charge of a battery, and you can already see that since it has a very high bulk sensitivity and it uses very high energy X-rays, we can do in operando measurements, which is not that easy to do with other experimental techniques. Next, I will briefly discuss how Compton scattering technique can be used to understand an atomic level picture of the redox orbital in battery cathode, such as popular lithium iron phosphate. Here, using AB initio calculation, we developed a method to model Compton profile difference between two lithium concentration in lithium iron phosphate. Actually, in lithium iron phosphate, you only have two different phases, and we use that two different phases and take their Compton profiles, take the differences, and from there we get this new quantity called difference Compton profile. And here you can see that there are different models, but the best model is this green curve, which actually reproduce this experimental, this red curve behavior very well. I'm not going to go over details here, but briefly in few words, the key takeaways from this previous work was like, this kind of analysis reveals a new link between voltage, the localization of transition metals, like for example, the localization we find from using Harvard U, and and also the how that is related to the kinetic energy change due to a lattice distortion happen when the lithiums are moving from the cathode. And we then construct a descriptor that connects voltage shift in battery cathodes to the metal oxygen bond oscillation. This modification of the bond between the transition metal and oxygen atom is also related to a volume change of the unit cell, which shows a decrease in volume change as we go from manganese to nickel. And as a result, we see a reduce in the voltage shift. So interestingly, you see that like this bond oscillation, it is also of course related to the like overall volume change. And then what we did is we tried to gather some previously reported reported results in different literatures. We also find a similar trend that as if there is any literature where the iron is partially substituted with manganese, cobalt, or nickel, we also see the similar kind of trend. My third example is a magnetic Compton scattering study where we try to understand the capacity fading issues in spinel type of materials such as lithium manganese oxide. This capacity fading is related to an antiferromagnetic phase, which shows strong charge ordering for a fully lithiated sample. And we have like this kind of antiferromagnetic spin arrangements. The first layer is manganese 4+, but all of them are up. The third layer is manganese 4+, but they are down. In between, you have manganese 3+ up-down spins. And this particular phase is very stable. So what happens is, if you have these batteries and you discharge it, you charge it or discharge it, and it goes to this phase, it just stuck there. So therefore, what happens? It doesn't, the cathode doesn't work anymore, and that's why we have some capacity fading issues. So we need a battery that has reversible process, right? It can goes from one phase to the another phase without any issues. So we have some issues here, and we try to use magnetic Compton scattering to understand this phase. And we actually found that, we were actually able to visualize the manganese T2G orbital in this case, which can be used to investigate the change in magnetic phases at different lithium concentrations. And we found a robust ferromagnetic phase right next to this antiferromagnetic phase that reduced the overall charge ordering and corresponding capacity fading issues with cycling. Now, I will discuss about my work on the lithium titanium manganese oxide. And I think at this point, I am able to convince you that the Compton scattering is a very powerful technique that can be used to understand key battery characteristics, both at macroscopic level and at the atomistic scale. I will now discuss how this technique can be applied to lithium-rich materials and how the electronic orbital that lies at the heart of the reversible anionic redox process can be imaged, visualized, and its symmetry can be determined. So here is the detail of our electronic structure calculation. We perform DFT calculations on the LTMO structure, which is a cationic disordered rock salt. As you can see here, by cationic disorder, I mean like here all these manganese, lithium, and titanium, they actually share the same lattice site, and there is a disorder in this case. They do not follow any particular order. So some details are here. We performed we performed the DFT calculation and then use the POC Onsham orbitals and calculates electronic momentum density distribution. And after performing a spherical average on this momentum distribution, we get this one-dimensional or two-dimensional parameter, that is the Compton profile. We can make it one dimension if we make it if we integrate it in two different directions, and then two dimension if we just choose two directions and plot it in a two-dimensional way. Here shows the calculated Compton profiles for LTM with different lithium concentrations. What exactly it means, I have been talking about this, but here this is the Compton profile on the y-axis, and x-axis is the momentum. So this basically gives you this distribution is give you all the electrons, the momentum distribution of all the electrons below the Fermi level. This is how I can say. And you can see that we are increasing this lithium concentration. That's why we see some increase at the peak because of that. And why? Because of that, because we are right now we are in the momentum space. So therefore, what we realize in real space is kind of opposite in momentum space. In real space, the lithium is kind of delocalized, but in momentum space, it is localized. That's why we see some increase at the very low momentum due to this concentration change. Now, this type of picture is not that useful because we only see that there is some change in the zero momentum. A more useful way to analyze this is taking just taking two of these concentrations, two of these distributions, and take their differences. Like for example, here we take 0.8 and 0.4, and we just take their differences, and this is how we can focus very close to the Fermi level, because now all the contributions from the deep valence bands or the core are now cancelled out, which are not useful in this case, because it is only the electronic states that's near the Fermi level that participates. And from there, we can now compare their shape with the atomic profiles. Like for example, here, the blue curve is the atomic oxygen 2p, yellow curve is atomic Compton profiles for manganese 3D. And we can compare now these two with this derived and the experimental profiles. And you can see that at low momentum, it is mainly oxygen 2p, that is the behavior is more like oxygen 2p, but the long tail is coming from manganese 3D states. Now, we then compare this with the spinel type of materials such as lithium manganese oxide and lithium rich LTMO. We compare these two different samples. We find that the behavior is more or less similar. Even lithium manganese oxide, here we choose x equals to 1 and x equals to 0.5. We see that also the low momentum area is similar to atomic oxygen 2p. The high momentum is coming from manganese 3D again, but there is a subtle change. Here we see this kind of negative excursion, which is not absent here. In fact, here we see this kind of shoulder. So that is the difference, and we try to find out why they have these two different differences, because in both cases we have oxygen 2p and manganese 3D, but they are different, right? And we try to find out why they are different. So first we take this spinel lithium manganese oxide, and we construct this manganese atomic Compton profiles from our theory, and we found that some manganese electrons, this negative excursion is responsible for some manganese electrons transferred from localized to less localized 3D states. and we can find out how much electrons are transferred from, how much electrons are responsible for this kind of manganese orbital delocalization, and what happens due to this delocalization. So now these manganese orbitals are delocalized. Now they actually, because of this delocalization, they interact with the neighboring oxygen orbitals and make this kind of covalent bond that we have discussed earlier. On the other hand, in lithium-rich LTMO, we see an opposite trend. Instead of negative excursion, we see a shoulder in redox orbital. And in this case, we can explain this long tail if about 0.19 electrons from the manganese 3D shell transfer from the less localized to more localized 3D states. So we have a localization happening here on the manganese side. And we find that this localization is produced by the Coulomb repulsion between an occupied state at the oxygen site and the 3D states in the neighboring manganese ions without a significant formation of a covalent bond. And we in fact did thorough study of electronic structure, and we find that we can also consider the formation of this upper Hubbard band and this lower Hubbard band, where the lower Hubbard band stays close to the occupied oxygen states. The presence of these occupied oxygen states can be observed in also in partial density states, where the localized oxygen 2p states point in a direction of a neighboring lithium atom. Therefore, this Coulomb repulsion between the electrons in the lower Hubbard band and occupied oxygen non-bonding state next to it is responsible for this manganese electron localization. So this provides a conclusive evidence on the formation of non-bonding or orphaned oxygen orbitals in a lithium-rich materials, which is responsible for this anionic redox and related high capacity. Next, I will discuss the two-dimensional momentum density representation of the redox orbital. Here is an earlier work by Professor Bansil and his group. Here in this work, they visualize the redox orbital in hole-doped cuprate superconductor, which shows the momentum space representation of the copper oxide plane in this material, in this lanthanum strontium copper oxide. This maps gives you some information about the extent to which these solid state orbitals are modified by the chemical bonds. And we see an inverse relationship between real space and momentum space representation. Here, the low momentum contributions are coming from these oxygen orbitals, which are delocalized in the real space, and the high momentum contributions are coming from the copper dx square minus y square, which are localized in real space. So you see there are some inverse relationship between this momentum space representation and the real space representation. And these are actually some nice experimental plots for this momentum density. And you can get this kind of momentum density plots if you have a single crystal and you take the different directions and of course different doping concentrations. And in this case, the directions are px and py. And you take the differences, you will find this kind of atomic resolution, atomistically resolved picture for the electronic state. Now, for the LTMO cathode, it is not possible because the LTMO cathode is composed of polycrystalline powder sample. Most of the battery cathodes are actually powder samples. Therefore, we cannot have the single crystal and we cannot perform the experimental spectra. And as a result, we reconstruct this angular dependence of the redox orbital using spherically averaged Compton profile. We already saw that the repulsive Coulomb interaction produced a substantial localization of oxygen 2p orbital in real space, and which we can realize through this delocalization of oxygen 2p states in momentum space. This shape like the sharp box like features in the on the LTMO in the high momentum like this. You can see a sharp box like figure here. This is actually associated to the Fermi surface breaks related to localization of manganese T2G bands that can be extracted by performing magnetic Compton measurements. We actually have done this for LMO earlier, but this is actually just not the magnetic picture momentum density. This is actually the redox orbitals that can be visualized from the theory. And you can see that we can these two pictures are really different. In this case, we have some localization in momentum space. That means in LMO we have actually delocalization in real space, as we discussed earlier. On the other hand, here the oxygen states are very localized but delocalized in momentum space. That's why it is kind of spread. And this from these two picture, we actually find that this kind of representation could be a very good descriptors for the battery materials, like how much they are delocalized or how much these oxygen orbitals are delocalized. And because of that, you see this these edges of this sharp box, these are actually the position for the T2G orbitals. We actually did this earlier for a different project, and we found the location of these T2G states. And from there, we can also find out how much T2G electrons are localized because of this this kind of localization of oxygen states nearby. And this gives an overall picture of how this oxygen 2p states that is non-bonding and how that is participating with the neighboring oxygen these oxygen states that is not participating in the any kind of covalent bond formation, but it is actually participating in the redox process as like an atomic orbital, and that is also influencing the neighboring manganese site. And this kind of picture was not realized previously for this manganese for this oxygen non-bonding state and the corresponding high capacity that this non-bonding state offers to this kind of materials. And we for the first time realized this using theory and experiment, and we published this paper in 2021 in Nature. So this is actually, I think I can give you, I was able to give you some idea about our effort in Compton scattering and how we use different materials over the time to understand the atomistic insights or the quantum mechanical insights that we have developed. We also developed various descriptors. By descriptors, it means like it has materials and property relationship. So for using that descriptor, we can identify some key values, or some key features of some materials. And in the future, we are actually right now working actively on some perspective on the machine learning, because we have developed various descriptors. We want to use those descriptors. We have been also developing various database. So we have a database full of various electronic structure calculation, various structural descriptions, and also we have derived various descriptors. We try to find out some complex relationship between them. And in the future, we want to solve some of the issues in the current battery industry, using some new techniques such as artificial neural network. So this is just to give you some future outlook, what we have been pushing on right now. Otherwise, here is the summary and conclusion. We understand that there is some serious issues in the battery industry right now. First of all, the current technology is very poor. We need to have some very good insights. We need to use a spectroscopic technique. We need to use very thorough calculation, and we need to understand even more how a battery material works and how we can design new ones. And of course, here we see that the anionic redox is one possibility. And we now have very good understanding of this anionic redox, which can be immediately used for next very next generation of batteries, or like electric aviation probably. But there are like associated problem. For example, the safety issues is one of the problem which we still need to understand. You can see that there are a lot of oxygens are participating in this kind of anionic redox. So which means like there is an issue of a fire issue of this because of this oxygen participation. So we have to see how we can make this reversible without any issues of the oxygen form or like release for this redox process. And finally, we have to use, of course, we have to predict new battery materials, and an effort actually globally there is an effort going on in material science using applying machine learning and like they accelerate the pace of discovery. Here is some acknowledgements for my advisors, mentors, PI. The work was actually mainly funded by US Department of Energy, and I have also used computational resources from various sources. And with that, thank you very much for your attention and for giving me the opportunity to talk here today. And I'll be very happy to answer if you have any questions.
Thank you, Dr. Hafiz. It was very informative. The talk was really informative. And I think this is one of the burning topic in the scientific community right now. So we now open the session for a discussion. So any question you have, you can please put up your question. Dr. Hafiz will be happy to answer your queries.
May I audible?
Yes, yes.
May I ask a question from Hafiz, Professor Hafiz?
Yeah.
Yeah, thank you, sir, for your informative and very nice talk. And I've learned a lot. And with this, I have a question that, could you please let me know that which topic in the energy store material is emerging, and there are gaps in that particular research area and that we can cover?
Yeah, that's a very good question. So there are a couple of challenges right now.
Yeah.
So for example, let me just show you here some challenges. For example, there is one issues with these materials that I just described today. This lithium titanium manganese oxide is their capacity fading issues. So by capacity fading issues means like so it undergoes some kind of structural change, right? Because you are removing the lithium, and these lithiums actually has a very disordered phase with the titanium and manganese because they share the same side. So what happens during charging, discharging, these lithiums comes and backs, but they may not come to the same same position. They will come to the same lattice side, but they may not come to the same positions. So there might be a possibility that they do not fully retain itself once it removes and then comes back, or like it just stuck to some atomic sites where we cannot move them anymore. So what happens over the time, this makes some capacity fading issues, and this is actually a voltage hysteresis, as you can see here. There are ways you can reduce it. Like for example, people have been using this like 5D materials. So if you go from 3D materials to the 5D materials, there you can actually reduce this kind of voltage issues. But there is also problems of sluggish kinetics, because what happens is you have this electrolyte, and these lithiums are kind of diluted inside the electrolyte, and this electrolyte it is actually ion conductor, so it moves these lithiums from anode to the cathode. So if there is a rate change of this, if there is you have to maintain a certain diffusion rate of these lithiums through this electrolyte. So they also show some kind of using this kind of materials, you can have very sluggish kinetics. So this change will be very slow, and that will also can produce this kind of capacity fading issues or voltage fading issues. On the other hand, if you have a very high rate diffusion, that is also a problem, because in that case, this will decompose on the electrode and will make some it will crack the electrode at some point, and we'll have all the fire issues and other issues. So safety issues is one of the very concerning things. And as I mentioned, it is not fully solved. We still need to make a high capacity electrodes that has very good reversible behavior, and that also has stability. So safety and stability is probably the two different issues that we should concentrate for some kind of future study.
Oh, thank you very much. Thank you very much.
Any more question, please, if you have?
Sir, I have a question. Hi, Hafiz. It's me, Rai.
Hi, Dr. Rai, how are you?
Yeah, I'm fine. Yeah, I just want to know, in this alkali group, elements, why this lithium is particularly chosen?
Okay.
Can it be used other alkali elements?
Yes, of course. But there are some. That's a very good question, actually. So there are some good reasons why we choose lithium. Because there are batteries with sodium, for example. But the sodium size is, of course, bigger than lithium, right? And the main reason we are with the lithium technology has developed over the years is, of course, the lithium is a very good, very interesting metal, but size-wise, it is also very small. So we can make a battery smaller that we can put inside your laptop, or you inside your cell phone. At the same time, you can make bigger batteries for electric cars, but the overall the weight will be less, right? If you let's say if you want to make the same capacity batteries, or same size of kind of performance using sodium battery or magnesium battery, you have to make a very big battery, and the weight will be also very big. So that's why for those batteries are mainly used for grid purpose. Like, let's say you have solar panels in your roof, and you harbor all the solar powers, and you want to collect them, right, for night or for other days. For those purpose, for those kind of storage, you do not care about the size of the battery. You can just put it anywhere in your house. So in that case, we use sodium batteries, magnesium batteries, and some other alkali materials you can use. But for the portability, for the ease of use, for making very lightweight electronic devices, that is actually the main motivation. The lithium battery technology is still evolving.
Okay, thank you. So one more question. It might be a stupid question, but can I ask one more question?
Yes.
We have been talking about the solid state batteries, and we also know that liquid state batteries are also there. Is there any possibility of gas state batteries, with the hydrogen
not gas
atom?
state, but so there are already some lithium metal batteries are already there, where the anode is fully just the lithium metal. The gas state, I do not quite sure about that, but the reason why we use liquid batteries is because of this safety issues. The liquid batteries are actually way more safer than the solid state batteries, because in liquid state, the electrolyte is mainly water or water derived material, where in the solid state we have used electrolyte, which by electrolyte I mean the ion conductor is some kind of other chemicals and polymers which are not very safe in many research says. So the liquid battery use this water, and then that's why you have this window where you can have hydrogen evolution, oxygen evolution if you go to a higher voltage. But in between, you can find a good window where it can be stable. But the voltage wise, the liquid battery is very low. That's why the liquid battery is only used for certain purposes. But for the gas state, I'm not sure about how will you do the this electrolyte or the ion conductor. But I would say I do not have enough idea, but it would be might be possible at some point. Yeah, but the thing is, our main concern is actually somewhere else, where it's how much lithium we can actually have in a certain batteries, because that is one parameter, because those lithiums we can then move, and that will give you the direct way of capacity, or how many electrons are involved in a certain redox process. That is also give us some determinating factor for the capacity. So that is actually the main concern. If people can do that with the liquid batteries, I think people will go for the liquid batteries because that is more safe. Yeah.
Thank you.
Sure.
Hello, sir. That was an insightful talk, sir. So I have a basic query. What is your take on hydrogen fuel cells, sir?
Oh, okay. So yeah, I as earlier I was introduced, I have been also working on the hydrogen fuel cells as well, and there are reasons why we are using hydrogen fuel cells, and one of the very good reasons is these batteries. These are interesting, and these are promising, and I'm pretty sure the battery industry will thrive next at least next 50 years or so on. But you can see that everything boils down to the cost of the raw materials at the end, and that is one of the motivation. That's why we are pushing toward less expensive but highly abundant materials. But this will cost at the end, this we will have the shortage of raw materials, because the demand will also increase exponentially. After a few decades, this increase, the demand will be even higher. The reason why we are pushing this hydrogen fuel cells research, because we want to make something more environmentally friendly. The batteries industry is not actually 100% zero carbon emission. It is actually a lot of carbon emissions happens during the process of these batteries. So it is not entirely zero. It is of course better than the gasoline, but it is not 100% purely green energy. But on the other hand, hydrogen fuel cells is purely green, and the reaction is very simple. There are some bottleneck going on in the stability of different fuel cell cathodes, especially on the electrocatalysis part, where we need a lot of precious catalyst, which are expensive as well. But we will try to solve with the less expensive catalyst. And the water is abundant in our art, right? So we can use that. And from the earlier questions, that what are the challenges? One of the challenges is also in the fast charging of batteries. So currently you can use supercapacitor charge stations, and where for example a Tesla car takes at least 45 to 1 hour to fully charge. Now, if you go to your gas station, your petrol station, you just think about if you need to stay there 1 hour to fill up your tank, how painful that will be, right? So we do not want that either. And these fuel cells like, let's say in 20 years later, we solve some kind of some bottlenecks. We solve some of the issues of the present fuel cell industry, and we have set up all the stations everywhere, and it will be just, our life will be way easier, right? And fuel cell, technically, it can achieve, like, the energy density as good as batteries. So it will be safe. It will be like, our life will be much easier, and like, we can use the most abundant like, the material of Earth, which is the water, and it will be like, the green energy wise, it will be very good. Yeah.
Thank you, sir.
If there is no more questions, I think I should thank Dr. Hafiz for a very, very interesting talk. We really enjoyed your talk. I think the participants here will also vouch with that. And I hope that we can have you in our midst sometime later also, when we organize this kind of seminars again. We may request you to give a talk to us. We really enjoyed listening to you, and I hope your work on the lithium ions will produce better batteries in futures. With this word, I thank Dr. Hafiz. And dear participants, now we'll be going straight for the closing function, because this was the last talk of our conference. So we'll go for the closing function, and I request you to be with us. And for the closing function, our chairperson is Dr. Lalchit Jwala, the convener of the program. So he will be the chairperson, and he will be joined by our principal of the college, who will be as the guest of the function. So may I now invite Dr. Lalchit Jwala to take over and conduct the closing function. Thank you, everybody.
Thank you.
Okay, so I hope I'm audible and the PowerPoint that I share here is visible to everyone. So we have now come to the end of our 3 days international conference on material science and applied physics. And it has been really a fruitful experience for us, the department who are organizing this conference. And I hope it would also be a very fruitful exercise and academic discussion for every one of us who are participating from the very first day. And yeah, there are a lot of, I think, a lot of things that we might want to ponder on, and we might want to continue our focus after this conference. And I really hope that this kind of conference will bring every one of us together for better research collaboration as well. So our program, as shown here in the screen, will be a very brief program, and we will hear a report from Dr. Divya Prakash Rai, who is also the convener of this conference, and he is the one who has actually made all this arrangement. So I shall now invite Dr. Divya Prakash Rai to give a report of our conference.
Thank you, Chairman, sir. Respected Principal, sir. I'm going to report about our conference, International Conference on Material Sciences and Applied Physics, which was held from 22 November to till today, 24th November 2021. Sir, this program, finally we come to the end of our program, and this program was very successful, I should say, because this is our first international conference, even though it is in a virtual mode. But the good thing is that we have got around 155 participants from all over the world. And we have around 18 speakers, and all the talks, all the invited talks and all the technical sessions goes fully attended, and none of the speakers were absent, and none of these slots goes off. All of them were there. They devoted their time. They gave their time despite of having busy schedules. They came and they gave their talk. And for our special chief guest, we have invited Dr. Varsane, who is the head and advisor of International Cooperation Division, Department of Science and Technology. Though he could not give his first talk, but he managed to give the talk on the second day. And on the second day, the inaugural address was given by our Honorable Pro Vice Chancellor, Professor Patnaik. Then the talk was followed by our patron, who is the VC of Central University of Haryana. Then we had a number of, then we have invited talk from Dr. Mahesh Kumar. Dr. Mahesh Kumar from IIT Jodhpur. Then we had 6 continuous invited talks. Then after that, we had a special talk again at 6:30. And this talk was delivered by Professor Sugata Chaudhary from Howard University, USA at 6:30 p.m. And on the next day, again, we started with the keynote speech, and that was delivered by distinguished professor in physics, Professor Arun Bansil, who is also the editor and the founding members of the Journal of Physics and Chemistry of Solid, Elsevier. And he delivered his talk. And after that, the talk was, then after that, we had a plenary talk from our chief guest, who was absent in the first day. Then we had 6 speakers gave their invited talk. Then again in the 6:30 p.m., we have arranged another speakers that was given by Professor Robert Iglitis from Latvia. On the third day, today, in the final day, our keynote speakers were Professor Madhurima, who is also the former faculty of Mizoram University. And second keynote talk was delivered by Professor Manish Kumar from Jawaharlal Nehru University, JNU, New Delhi. Then again, we had a 6 talk. None of the talk goes off. All were attended. And finally, in the 6:30 p.m., we had a special talk from Dr. Hasnain Hafiz. And just now only he has given his talk. And altogether, we had 155 participants, and maximum from our own country, 125 participants were there, and 13 were from Pakistan, 10 were from Nepal, 6 from Algeria, 2 from Kenya, 1 from Poland, 1 from Egypt, 1 from Morocco, 1 from Palestine, 1 from Taiwan, 1 from Dubai, 1 from Vietnam, and 1 from Japan. And among these speakers, we had 3 speakers from United States, 11 speakers were from India, and 2 were from Nepal, 1 from Kenya, 1 from Russia, 1 from Taiwan, 1 from Turkey, and 1 from Sweden. So this is the report that I'm submitting. So I'm sorry that I could not make the PPT because I was busy handling all the sessions and all. And I would like to thanks to Dr. Sheta. Dr. Sheta is a very busy person. He was involved in the college also, and he was involved in the conference also. Despite of his busy time, he has helped me a lot. We have worked together. We are trying our best to give for the resource also. And for this conference also, he has worked very hard. And I give credit to all my colleagues, our chairman, sir, he was there for chairmanship for all the 3 sessions, 3 days. Dr. Sivraj Gurung and all my faculty friends, they supported me a lot. And not the least is our very dynamic principal, who is also a very dynamic researcher, scientist, and who has always encouraged, motivated us. And this is the result we have, and we are giving to you, sir. Thank you. Over to you, Seta.
Thank you, Dr. Divya Prakash Rai, for a very detailed and very important and reports. Within a very short span of time, he highlighted all the important points that are needed to be highlighted in this conference. I think we all are very grateful to our main organizer, Dr. Divya Prakash Rai. So now now it is time to invite our principal and who is also the patron for this conference. And as mentioned by my colleague, Dr. Divya, he has been very helpful in organizing this conference. So I think we shall now give time to our principal.
Thank you, our chairman, Dr. Shriyata. First of all, a very good evening and maybe good morning from some other parts of the globe to all of you. This is a very important time, a very remarkable time for the Pachu University College, as it is being the first international conference organized by the Department of Physics. The first international conference on material sciences and applied physics 2021. I am out of station for a while because of some other administrative official duty. I've been out of station for 2-3 days. But anyhow, the department and the coordinators are successfully coordinating and organizing this international conference. I'm very glad, first of all, to the organizers, the Department of Physics, the head of the department, Dr. Sivraj Gurung, the coordinators, Dr. Shriyata, Dr. Prakash Rai, and all faculty members of the department, the PG students as well. I'm very glad to the organizers, and also I congratulate them for successfully organizing this very important event. I'm very thankful to all the 155 participants from all over the world. Especially my sincere thanks to the invited speakers, all the 18 speakers of this international conference. I'm sure that your expertise and the knowledge you share to the participants would be of very interesting and very helpful for the participants. All the chairpersons of all the technical sessions, all the participants who have involved in the interaction and discussion hours. So I'm very thankful to all of you, all the participants who have made this conference a very, very successful one. As the head of institution of Pachu University College and the patron of this very conference, I am very, very grateful, express my sincere thanks to all of you. Your enormous contributions would definitely enrich the knowledge of the scientific community. As you know that it helps in the academic growth of the institution and also the academic collaborations. And I invite all the distinguished participants from all over the globes and the speakers, invited speakers, and eminent scientists who participate in this conference to initiate collaborative work in various fields that are discussed during the conference. The Department of Physics of Pachu University College, the faculty, we are open to collaborate with you in any kind of fields that we are that we can. I thank to the chief guests and the plenary speakers of this evening, this time, Dr. S.K. Varsni. I'm very grateful to all the expert and participants. It would be a very grand success because of your contributions and your expertise. Thank you all. And with that, I conclude my speech. Thank you so much. Thank you.
Thank you, sir. Your guidance and your encouragement is really appreciated. So before we conclude this session, I think I should now open I should now invite any participant or the chairperson or any invited speaker who is still here with us, if they have any comments. If any participants is in, if any participants or anyone wishes to have a certain comment on this conference. Okay, I guess probably the feedback session was already held in the evening. So before we conclude this session, I would like to say a few words, even though our secretary, our convener, Dr. Divya Prakash Rai, and our principal, Professor Aisal Tanzara, have already mentioned, we are so grateful to all the participants. And in organizing this conference, because of the participations from India and Pakistan, Nepal, Algeria, Kenya, Egypt, Japan, Latvia, Morocco, Poland, Palestine, Taiwan, UAE, Vietnam, I believe that this conference was really a success. And not only that, the invited speakers gave a very insightful speech in every session. The participants also contributed in the discussion. So for the remaining participants also who are not involved in the discussion, the discussions that were held during the talk, after the talk and all, I think it was really helpful. And I should also thank our chief patron, our vice chancellor, Professor KRS Sambas Sivarao. And unfortunately, he was not able to give his inaugural talk on the first day because of his official duty. But he has been encouraging us, and he has been guiding us for the success of this conference. And we are really thankful to our principal, our other professor who retired from Mizoram University, our other patron, Professor R.K. Thapa, and Professor Tankeshwar Kumar. In spite of his busy schedule, Professor Tankeshwar Kumar was able to give a speech in the inaugural session. And we are thankful to our chief guest, Dr. S.K. Varsni. In spite of his busy schedule, he was able to spend some time with us yesterday in his plenary talk, and the experiences he shared and the kind of issues he highlighted regarding the PhD supervision and research, it was really helpful to every one of us. And I also thank all the invited speakers who have dedicated their time for the success of this conference, and also the advisory committee member. Among our advisory committee member, Professor R.C. Tiwari and Professor Zaid Hanzawa Pachuo were able to chair the plenary talks and the keynote speech, So, and they have all been helping us in for the success of this conference. And I also thank all the 26 advisory committee members, Professor Gulmurza, Professor Oksana, and Professor P.K. Patra. Even though they did not deliver a speech, they have been attending the program and involved in the discussion. And I also thank all the local organizing committee, our chairman, Dr. Sivraj Gurung, and all our colleagues who have contributed a lot for the success of this conference. So with these words, I shall now declare that this conference is now concluded. Thank you, everyone.